Hello, and thank you for joining me on this brief discussion of a variety of mainly organic colors. This presentation is on the chemistry of color, dyes, pigments, and paints. Why do we see color? Color is not a property of objects. It is how our brains perceive certain wavelengths of visible light. The differences in wavelengths and structure determine the color we perceive. When a molecule absorbs specific wavelengths of visible light, it causes electrons to transition from a lower energy orbital to a higher energy orbital. We perceive the complementary color of what is absorbed. So, if a molecule absorbs blue, we see orange. Or, if it absorbs green, we see red. The size of the energy gap between the HOMO and the LUMO determines which wavelength, and therefore which color, is absorbed. The more conjugated a molecule is, the smaller the HOMO-LUMO gap, which means the lower the energy and the longer the wavelength absorbed. When pi electrons are delocalized over a conjugated system, the energy difference between molecular orbitals becomes smaller, leading to absorption in the visible range. Specifically, the colors we perceive are due to the existence and length of conjugated chains within a molecule. Structurally, those differences are also observed as chromophores, or conjugated systems, and substituents present. A chromophore is the part of a molecule that absorbs visible light, causing color. Usually, a chromophore is a system of conjugated pi bonds, double bonds, or aromatic rings. Conjugation allows pi electrons to delocalize across multiple atoms, spreading out their electron density. Substituents such as OH or NH2 can donate electrons into a conjugated system, shifting absorption towards longer wavelengths, a red shift, while groups like NO2 withdraw electrons and shift absorption toward shorter wavelengths, a blue shift. Electron withdrawing groups stabilize the LUMO, electron donating groups raise the HOMO. Donating groups raise the HOMO. Without a conjugated chromophore, most molecules are colorless, even if they have nitrogen or oxygen atoms. This is why simple molecules like water or ethanol are colorless, while complex molecules like beta-carotene are brightly colored. It is in all these differences in the energy gap that subtle chemical changes can create different shades within the same class of pigment. Tiny variations in chemical structure or even physical form change the way we perceive a color. One interesting example of this is the grain size effect. Grain size affects color. A substance that's finely ground appears lighter in color than the same substance coarsely ground, which will look darker and richer in color. In this example, finely ground azurite looks sky blue, coarse azurite looks deep violet blue. Chemically, the more scattering and absorption that occurs due to particle size, more the apparent color shifts. In summary, color in organic chemistry stems from pi electron conjugation and HOMO-LUMO gaps. Azo dyes are synthesized via diazotization and coupling and dominate modern dye chemistry. Conjugation, oxochromes, and substituents fine-tune the absorption wavelengths, which fine-tune the color that we get to see. Spectroscopic techniques enable pigment identification and conservation without damage to the art. Understanding molecular color helps design safer, more durable, and expressive materials in art, textiles, and industry. IR spectroscopy detects functional groups, like the double bond N or alcohol group in pigments, without destroying artwork. UV spectroscopy reveals absorption maxima, or lambda max, indicating conjugation extent and likely perceived color. X-ray fluorescence and Raman spectroscopy help identify pigment composition in art conservation and forgeries. Azo dyes are a major class of synthetic dyes characterized by the N double bond to N or azo bond, linking two aromatic rings. It's highly conjugated and easily modified to produce a wide color range. These dyes are about 70% of all synthetic dyes manufactured globally. This is from Al Sayed 2024. They're popular because they're cheap, vivid, and easy to make. This group of dyes is used to directly color leather, silk, and other porous fibers like wool. One example is Acid Violet 1, as you can see below. Azo dye synthesis. The majority of azo dyes are made by diazotizing. Diazotization is a chemical reaction where an aromatic primary amine reacts with nitrous acid to form a diazonium salt. This unstable intermediate then couples with an electron-rich molecule like phenol or aniline, forming the brightly colored azo compound. This simple reaction, discovered in the mid-1800s, unlocked a revolution in industrial dyes. Most azo dyes are synthesized by diazotization, followed by coupling with one or more electron-rich nucleophiles such as amino and hydroxy. This azo group may be bonded to benzene rings, naphthalines, aromatic heterocycles, or to enolizable aliphatic groups. These are essential to give the color of the dye, with their shades of different intensities. In general, the chemical structure of an azo dye is represented by a backbone, the oxochrome groups, the chromophoric groups, and the solubilizing groups. The color of the azo dyes is determined by the azo bonds and their associated chromophores and the oxochromes. This is from Benkhaya 2020. No natural dyes contain this chromophore. Before 1865, purple dye came from sea snails. It was expensive and elite, but Perkins' discovery of mauveine, the first synthetic dye, changed everything. Thanks to the Industrial Revolution, synthetic chemistry became practiced more, leading to artists and common people having access to the vibrant, affordable colors. Now we will be looking at chemicals being used in paintings, pigments, and how they tell a story, and how some of those paintings look today. Now we'll be looking at Egyptian blue, also known as calcium copper silicate, which originated in ancient Egypt and is said to be the first synthetic pigment. It was and still is an adored and fairly commonly used color due to its high stability and beautiful and permanent blue pigment. Next we see lapis lazuli, or ultramarine blue. This is a natural pigment that came from Afghanistan, and it contains lazurite. This is from Church 1970 and Department of Chemistry. And to prepare this pigment, selected pieces of small size, as free as possible from pyrites or other impurities, are heated in a crucible and quenched in cold water or very weak vinegar. We can see lazurite or ultramarine being used in medieval art, such as the Wilton diptych from 1395 to 1399. It is a brilliant blue. This color comes from the silicone radical trapped inside the crystal lattice. It was very expensive, and artists in the Middle Ages and later would sometimes scavenge the blue pigments from paintings to use in new works. It was especially desirable for use in robes of religious figures, most notably the Virgin Mary in Christian paintings from the Middle Ages and Renaissance. In the 1800s, a synthetic version was created known as French ultramarine blue. As a result, the discovery and expense of the natural mineral lapis lazuli dropped out of favor, and the pigment was no longer referred to as ultramarine. However, it can still be purchased from specialty painting supply stores. The next pigment we're going to look at is emerald green. Emerald green is also known as Paris green or copper II acetoarsenite. It is a vivid color but highly toxic due to the copper arsenite. Emerald green is soluble in acids and alkalis, and can also be hydrolyzed by prolonged contact with water. This pigment was discovered in 1814 during the course of an experiment made with the object of preparing an improved Scheele's green. It has been valued by the painters of the 19th century for its vivid and excellent stability. Later on, production was halted, though, due to the extreme toxicity of the pigment being discovered. The pigment is not very light-fast. Emerald green darkens in contact with sulfur compounds, such as cadmium sulfide or cadmium yellow. I imagine this made it quite difficult to use in combination with other certain colors in paintings. Below we see an FTIR spectrum for Paris or emerald green. Although it was extremely toxic, according to Artrageous 2017, it was used in everything from artist paints to nursery wallpapers for over 100 years. Cadmium orange and red can be prepared by a reaction of a solution of a cadmium salt, such as cadmium chloride, with a solution of sodium sulfide and sodium selenide in the desired proportion. We see cadmium red in Henri Matisse's Interior with Black Fern from 1948. Cadmium red is made from cadmium salts and selenium. It has strong IR absorption due to carbon double bond to oxygen. We see below cadmium red before and after being mixed with linseed oil. Here we see the IR spectrum of burnt umber from Sennelier. Burnt umber is the general designation for a sedimentary mineral substance containing between 5 to 20% manganese oxides and hydroxides and a larger percentage of iron oxides. The higher content of manganese oxides compared to ochres is responsible for the brownish color. The calcinating or burning corresponds to heating the material with the purpose of removing water molecules from the crystal structure. This procedure results in a shift of color towards warm brown. Next, we look at black. We look at Mordant Black 17, a monosulfonated aromatic azo compound. This is a chromium complex azo dye, widely used in a large scale by several textile and dyeing industries. Next, we look at aniline black, which is an organic black dye from aniline oxidation. It creates a very vivid, or rather, a very dark and absorbing black. But it's not as black as Vanta Black. Vanta Black is an acronym for Vertically Aligned Nanotube Array Black. Vanta Black is a very modern black pigment made of basically a forest of vertically aligned carbon nanotubes. The light falling on the coated material enters the space between the nanotubes and is repeatedly reflected off the nanotubes until it is absorbed. Materials coated with this pigment absorb 99.965% of incident light, which made it the blackest known pigment at the time of its discovery. The chemical stability and light fastness of this pigment are exceedingly high. However, this can be easily damaged. The coated material has to be protected from touching or any possibilities of abrasion due to the delicate structure of the carbon nanotubes, which create a very thin and velvety surface. It is the darkest shade of black that we have available for painting, and it has been deemed for use of only military and astronautical companies. This color is unavailable to the public. I tried to get a sample for this presentation, and I discovered that it is about €460 for a sample. Vanta Black was first developed by a British manufacturing company, Surrey Nanosystems. However, an artist named Anish Kapoor bought the exclusive rights to Vanta Black in 2014, making it completely unavailable to the public. Here we see a large sheet of black velvet and the forests of carbon nanotubes or Vanta Black fragments that this scientist has created. Here we see two different sculptures, one of them being painted with Vanta Black and the other in its original form. Typical coating properties include ultra-low reflectance, UV visible and IR absorption, super hydrophobic quality, and very high thermal shock resistance. We see cinnabar used in The Assumption of the Virgin by Titian from 1516 to 1518. Cinnabar, or vermilion, is a toxic and dense red, also known as mercuric sulfide. When used as a pigment, cinnabar or vermilion darkens to gray or black. This has been attributed to reaction with chloride ions, most probably arising from exposure to humans. The initial reaction of mercuric sulfide with chloride is thought to produce corduroit, which then decomposes into calomel, and a cubic form of mercuric sulfide called metacinnabar, which is black. Below we see cinnabar, the brightly colored red compound, as well as metacinnabar, which is its black counterpart, is Jackson Pollock's mural from 1943. In this painting we see 7 different colors used, those including cadmium yellow, phthalocyanine blue, cerulean blue, vermilion, umber, phthalocyanine green, and white cason household paint. According to Colorlex, the ground is zinc white and lead white. You can identify where some of these colors are thanks to the numbers shown on top of the paintings. Next, we look at this beloved painting, The Starry Night, by Vincent van Gogh from 1889. Pigment analysis, based on the work of scientists at Rochester Institute of Technology and the Museum of Modern Art in New York, employed a method of multispectral imaging to prepare maps of individual pigments through the whole painting. They say the deep blue sky surrounding the stars is predominantly artificial ultramarine. The brighter blue swirling sky and the area surrounding the moon are predominantly cobalt blue. The green strokes around the moon are emerald green. The deeper yellow of the moon and the stars are said to be Indian yellow and zinc yellow, and the brighter yellow surrounding the stars and the moon is possibly cadmium yellow. Indian yellow, which is made from calcium and magnesium salts of euthantic acid salts, derived from cow urine from cows that have been fed mango leaves. However, this has been banned due to ethical concerns. This color is moderately stable, however it's highly non-lightfast, meaning it fades very quickly. Brown branches of the cypress tree at the bottom of the painting are burnt umber, and the green of the cypress tree is possibly Prussian blue and either burnt umber or one of the yellow pigments. In recent times, physicians have speculated that some of the illnesses of famous artists may have been the result of poisoning by their materials. For example, Dr. Bertman Carnot has suggested that Van Gogh's insanity may have been caused by lead poisoning, and has theorized that the blurring of stars and halos around lights in Van Gogh's later painting may have been a result of swelling of the optic nerve, a possible effect of lead poisoning. There is documentation of instances of Van Gogh swallowing paint and of his very sloppy painting technique. He was known to use lead-containing Naples yellow as well as other highly toxic pigments. While advanced technologies aim to control and prevent the degradation of cultural heritage objects in line with preventative conservation measures, there is much to be learned in terms of the physical processes that led to the degradation of the synthetic polymers that form the basic of acrylic paints largely used in contemporary art, says Ishan from 2021, who also says acrylic paints have been widely used by artists since the 1900s because of their many desirable properties over traditional oils, such as fast drying times, solubility in water, and applicability to different surfaces. I leave you with this from McCann 1979. The lack of awareness is more dangerous than the chemicals themselves.